words just for introducing Professor Bernard Derrida. I think that everybody, all the participants know Bernard Derrida because of he's a very worldwide renowned expert of statistical mechanics. And he is presently professor at the Collège de France, where he holds the chair of statistical physics, and he's also a member of the Département de Physique of the École Normale Supérieure in Paris. All of you know that Bernard gave a very important outstanding contributions to the study of disordered systems, out of equilibrium statistical mechanics, complex and biological systems, and many other applications of statistical mechanics. During his career, Bernard was awarded with many scientific prizes and acknowledgements, among which I want to mention the Boltzmann Medal in 2010. I want to warmly thank Bernard for having accepted our invitation as a speaker of this plenary colloquium online organized by the Italian Society of Statistical Physics. I am sure that all of us, and in particular our younger colleagues, will profit of the opportunity of attending his seminar on traveling waves and disordered systems. Thank you, Bernard, and it's your time for the seminar.
Okay, thank you, Roberto, for this kind introduction, and it's really a pleasure to have the opportunity to talk in this for the Italian Society of Statistical Physics. Okay, the only thing is that it's also very nice to be in Italy, but maybe it will be another occasion. So let me talk about, okay, the subject of my talk is about something I have been working on for about more than 30 years, and still I am interested in this problem, and I even published something a few weeks ago, so it kept my interest for many, many years. And I have, of course, collaborated on this thing with a number of people, so I will mention my collaborators, but the outline of my talk will be just to give you an introduction for people who are not really familiar with the subject, with what's called the Fisher KPP equation. I will tell you what it is, and I will mention what is how the velocity of these waves can be computed and can be understood, and then I will mention some very famous work for mathematicians by Bramson, who tells us what is the position of the front. Then I will mention more recent things about branching Brownian motion, what's called the NBBM, and finally I will talk about directed polymer. So all these things were done over many years, and my interest started with some work with Herbert Spohn in '88, and then, okay, so that already was an interesting time about these traveling waves. And then I worked with my student, former student Eric Brunet in Paris, and then there were some collaborations with Munier and Müller, who in fact are working in high energy physics, but similar equations occur there. And more recent works were done with Zhen Shi, who is now in Beijing, and Peter Motichon in Edinburgh, and Julien Berestiki, who is in Oxford. So let me just come to what the Fisher KPP equation is, and it is here written. And it was introduced the same year by Ronald Fisher, who was a biologist or a theoretical biologist and statistician, and by Kolmogorov, Petrovsky, and Piscounov, who were mathematicians. And it's this equation for a field which depends on the time and on the position x, say in one dimension. Of course, there are versions in higher dimension. And it was supposed to be a way to describe the following situation. You have some genes, for example, like the red ones, and the red ones have a tendency to replicate slightly faster than the blue ones. So what happens is that all these particles or these cells whatever particles they diffuse, the red and the blue, but that sometimes a red reacts with the blue to become two reds. And so the effect U is supposed to be the fraction in the population of red divided by the total number of particles at a given position. Just to simplify the discussion, I consider a situation where on each side of a lattice you have exactly n particles, and there are ever exchanges between the blue and the red, or reactions that sometimes when you have on the same side blues and red, then some blue become red. So this is the equation that they studied, and what you expect is that after a while, then the red will invade the blue region if you start with this initial condition. And the question is what happens in the long time limit, and then you will have a traveling wave moving. The red will invade the blue region, and then it will move at a certain speed. And this is the thing that you want to understand. Now, I am going to discuss two situations, the situations that Fisher and KPP study. Usually it's called the KPP by mathematicians, the Fisher equation by biologists, and physicists would call it FKPP equation. So what happens? Imagine if you make a mean field theory, like what the equation is a mean field theory, which is supposed to be true if you have a very, very large number of particles on each side. And much more difficult is what happens if on top of that there is noise, that is the total number of particles locally is not infinite, but is finite. And so what is the effect of noise? Okay, so this is a very old problem. As I said, it was started in 1937. And the first thing you can do, if you do, for example, you try to integrate the equation, you start with some initial condition, which would mean all the red are on the left of the origin and all the blue are on the right. After a while, and it will invade, and you see a traveling wave moving. And then what you observe when you solve this equation is that you get some shape which moves and does not change. The shape does not change. And then it moves at a certain velocity, and the velocity is close to 2. In fact, I will discuss a little later that there is another interesting velocity in this problem, which is a very negative velocity, that something happens very far to the left, although it looks that there is nothing interesting there, but in fact there is some interesting aspect very far to the left, moving at a different velocity. Okay, now what you see is a wave moving at a certain velocity, and then you can wonder what is the shape of this wave. And so you just take the Fisher KPP equation, which is on the top here, and then you say, you observe a wave moving at a certain velocity v, and you ask what is the shape of this wave, and then if you replace U in the FKPP equation, you get a differential equation for the shape of the wave. And it's nonlinear, so it does not look easy to solve. There is a velocity in this equation, and you can ask what is the solution, what is the velocity, how can you see this velocity close to 2 in this equation? And here starts the problem. In fact, this equation for traveling wave, there is not a single solution, but there is a whole family of solutions. And you see, the problem is nonlinear, so it does not look very easy to solve this equation for W. But if you make a very simple change of variable just to have a better intuition, then if you call W, you call it Y, X, in this equation, you call it tau, and you define a potential U, which depends on Y, which is like this, then the equation for the wave here is the same as kind of mechanical equation of a particle which is at a position Y in a potential U, and which has a force, which has a friction force which is proportional to the velocity. So solving the equation for the wave is exactly the same as solving this mechanical problem of a particle going downhill with a friction V. And you see, and it's at minus infinity, it's 1, at plus infinity, 0. So you start with a particle, and this particle goes downhill. And you can imagine, you see, for example, if you ski, that you can vary V, and you always find solution. If V is very large, then the solution will go down very slowly. If V is very small, it will go fast. Maybe if V is too small, then the particle will reach the bottom and then will make some kind of oscillation here, damped oscillation. But the point is that you have a whole family of solutions for each velocity. And then the question, which was raised these years, 37, sorry, was what is the velocity which is chosen? And so what is the velocity that you really observe? And the answer is the following, which has been known for very long, is that the velocity of the wave will depend on what you start with. If you start with a very steep initial condition, then the velocity will be the minimum of a function v of gamma, which is written here. This function v of gamma is very easy to obtain. You just think of, you look at what happens very far to the right, and you say, in the region where u is very small, then you forget the quadratic term here. So you have a linear equation, and you say, if in the tail it decays exponentially with some rate gamma, you put it in the equation, you just neglect the nonlinear term, and then you find that the velocity would depend on the rate at which the solution decays when you go to infinity. So this would be the velocity. And then the theory shows that if the decay is strong enough, if it decays fast enough, then gamma c, where gamma c is the place where this velocity has its minimum, then the traveling wave moves at the velocity vc, v of gamma c. And if it decays slower, then you would have another traveling wave moving at the v, which v of gamma, so it depends on what you have put in the initial condition. So this is, in very short, what people have known for very long about this traveling wave equation. And so you can think of it as a phase transition, because if you change the initial condition, then you change the velocity of the wave and the shape of the wave. But if the initial condition is steep enough, then you get always the minimal velocity, and the minimum of this function v of gamma is 2 for this equation. Now, in fact, the story I just told you would work for much more general equations. So the Fisher KPP is here, but you could consider equations with different nonlinearities, and under some conditions, which I have written here, under some simple conditions, you are sure that the same story will hold. That is, you look at what happens very far to the right, you consider only the linear part of f of u, and then this gives you the function v of gamma, and this way you can calculate the velocity of the front. And you can have more complicated diffusion terms, more complicated nonlinear terms, discrete time, and so on, and always you can find the velocity that way. Okay, now a very important contribution to this problem is due to Bramson, and maybe there was even an additional work by Eber and von Sarlos, who said that the wave is moving at a certain velocity asymptotically, but the position is not exactly vt. It's vt plus some logarithmic correction. And this 3/2, which is here, has been at the center of many mathematical works. You see, people have obtained it in many different ways, but there is never a very simple way of finding it. And more later, you see, about 20 years later, Eber and von Sarlos showed that if you continue the expansion, there is another term. And what is very important about this term is that they are universal. So if you give me the V of gamma of a problem, whatever problem you have, the velocity versus the decay of the solution, in the case of the FKPP, it was gamma plus 1 over gamma, then you can tell what is this term and what is this term, and they are universal. And for physicists, maybe I will just mention it in my conclusion, is that, you see, when you have universal terms, you would like to have some kind of renormalization group or something to understand them. And to my knowledge, this has never been done so far. Okay, now let me just say something about what happens with noise. And when you have noise, the story is much more difficult. The theory is much more difficult to do. But in 1997, with Eric Brunet, we made a prediction that when you put a small amount of noise, then the velocity is fixed, which is very strange. You see, when you have no noise, when the effect of noise was due to the fact, if you remember, that I have n particles on each side. So fluctuations become important. And one very first effect before any calculation is that you put a very small amount of noise and one particular velocity is selected. And the other effect, that's something that we predicted in 1997, was to say that if the noise is 1 over square root n, then the velocity is shifted by something like 1 over pi squared over log squared n. And okay, whatever is this result, you see, one thing is that it's non-perturbative in the strength of the noise. So it's not something that you can obtain by saying I make a perturbation in powers of a noise. It's more complicated, and this is our prediction. And you see, it's a hand-waving argument, which was which led us to this result. Later on, with Munier and Müller, we even computed, or we predicted the next term, and it took about 10 years that mathematicians were able to prove even the leading term. So the effect of noise is just to select a single velocity, and this velocity is given by this. And again, this correction is universal. So another prediction we had is that another effect of the noise is that the traveling wave is moving at a certain velocity, but the fluctuations will make diffuse this velocity. Now, what I should say is that these blue results there, both were obtained in 2006, but so far, mathematicians were only able to prove the red part, and the rest is under debate, and it's okay. So far, they have not been able to prove it. Okay, so let me just say very briefly what was the idea to get this result, and the idea is extremely simple. You see, okay, here, sorry, it should be C rather than U, but when you have this traveling wave with noise, remember initially I had n particles on each side, and U was supposed to be the concentration of red particle on the side. Now, the concentration of red particle cannot be less than 1 over n. So if you were looking very carefully at the system, the concentration would have some small steps. You see, it cannot be less than 1 over n. And so just because the minimum number of particles is 1 and there are n particles on each side. Okay, so the idea, what we did with Brunet at that time was just to say, okay, let's forget the noisy equation, which is too difficult. Eta is white noise. Okay, let's just say when the density is less than 1 over n or 5 over n or whatever, then we say it's 0. There is nothing anymore. So we solved a much easier problem where there is no noise. And then we replaced the nonlinearity by something which was 1 when nu was much larger than 1 and 0 otherwise. And this led to this correction. Okay, now this noise, the Fisher equation, in fact, appears in many other contexts. For example, if you would consider a reaction diffusion plus, you see, so A gives 2A, but then with a small rate, then 2A's would merge into a single particle. Then if the rate is very small, it would appear in the noisy term. Another situation will be the end-branching Brownian motion that I will mention later, where also the same story applies. Okay, now one problem in which the Fisher KPP equation appeared, it has been known for about almost 50 years, is what's called the branching Brownian motion. So we all know what is the Brownian motion. You have here space, the horizontal axis, and here it's time. And so a particle is moving like a Brownian particle. And then the branching Brownian motion is that at a certain rate, the particle splits into two particles, which themselves do Brownian motion. And then when a particle splits, the two new particles do exactly the same. So they do Brownian motion plus they split and so on. And so the typical thing that you see is a tree like that, a kind of random tree. And the place where the Fisher KPP equation appears is when you ask the question, where is the rightmost particle of this branching Brownian motion? You see, so it's the leader, but of course, with the leader changes with time because everything fluctuates. And so what is the probability of the particle, the rightmost particle? Now, it turns out that this problem, since the work of McKean, it's exactly the problem of the Fisher KPP equation. Where is the rightmost particle? And to understand it, it's rather easy if you ask what is the probability that the rightmost particle is less than x, then the idea is to think what happens during the very, very short initial time. So if you take the very first time dt, very short initial time dt, then what happens? Either there is no branching, 1 over 1 minus dt, there is no branching, but the particle has time to move a little bit by delta x, or there is a branching, and then for the maximum to be less than x, you need that now two particles, which are at position x, at position 0, will have their leader less than x. So you have q squared. And so now if you make this time interval very small, then you end up with an equation which is written down there. And this is exactly the Fisher KPP equation. You just make the change of variable 1 minus q, and it's a Fisher KPP equation. So from that, you know, and this is the work of Bramson, that the position of the rightmost particle will be 2t minus the 3/2 log t. You remember I said, where is the position of the front? So here you can tell that the rightmost particle, which its distribution is really given by the traveling wave equation, the solution of the traveling wave equation, then will be at the position 2t minus 3 log t. Okay, but there were other questions which were asked in the past, and I mentioned them briefly. You could ask about what's called large deviations. What is the probability that the rightmost particle is much more to the right than 2t? And in fact, it was proved already about 35 years ago that this decays that way. Okay, so for velocity larger than 4, it decays like this. And more recent works have been able to say things about the prefactor, which is much more difficult to compute. But something that we discussed with Zenshi, in fact, about 5 years ago, was to ask what is the probability that the rightmost particle moves less than 2t? What happens if the velocity is less than 2? So you have, that's nothing, the only thing you have to do is again to try to solve this equation and ask what happens when the velocity is less than 2. And the answer is that there is a phase transition at this velocity v star that I mentioned earlier. And this phase transition is rather easy to understand. Imagine that you start with a single particle, which does this branching Brownian motion, and this single particle, you want that after some time t, the rightmost particle is somewhere. It's not at position 2t, but it maybe could be at a negative position or something. So what is the optimal strategy to do it? To do it, it's shown by this picture. The particle you start with essentially does not branch for a while. So for a while, it does not branch. There is a certain probability for that. And at a certain point, it decides to branch in order to have this maximum particle, rightmost particle at a certain position. Now, when you do the analysis, then you get the following answer, that there is this velocity v star, and which says that maybe if you want to go very fast to the left, if the velocity is very, very negative, then the best is never to branch. And it's given by this expression. And if the velocity is between v star and 2, then what happens is that it's a picture I have just shown, that a fraction of the time it does not branch and then it branches. Okay, so this is what I wanted to say about the Fisher KPP equation. And now I come to a problem which is very, very related, which is called the NBBM, and the NBBM is just the N branching Brownian motion. And this was essentially something we worked on with Eric Brunet. There has been a number of developments in the last 20 years, especially among mathematicians. And the story is the following. So I told you what is branching Brownian motion. We have just, this would be this red picture here. But on top of it now I have a blue one. And the story is the following. Start with a branching Brownian motion, but now at each time t, you fix a certain number, you have a maximum number of particles, and then the size of the particle is, say, n, and then you want to keep this size fixed. You don't want the system to go beyond this number of particles. So what you do is that when you have a branching event, then you always keep the n rightmost particles. So the particle starts, and then some particle die. Whenever there is a branching event, you always kill the one which is the leftmost one. So this problem appeared in a number of contexts, but for example, one way to think of it is to say, okay, the horizontal axis is some kind of fitness axis. So the particles are like cells or bacteria or something like that. And then what happens is that the population cannot grow forever. So whenever there is a branching event, whenever the size of the population increases, then what happens is that you kill the one which has the minimal fitness. And then the system evolves that way. Now, if you want a picture, so here what I have drawn is on the left here is when I keep only 5 particles, and what you see is that the blue ones are moving, but if you look at it on a longer time scale, which is the picture on the right, then you have a kind of cloud blue cloud, which is moving, and it is moving less at a speed which is less than the speed it would have if n was, there was no selection, if n was infinite. If I would keep all the particles, I would have this red picture, but now because of this selection that I force the total number of particles to remain less than 5 here, less than n, then the cloud is moving slower because the leader here in the red, the leader is son or grandson of a particle, red particles which were eliminated before. You see, so okay, so this is the NBBM. And the kind of questions you can ask about this NBBM are the following. So you have this fixed population, and then you will have this cloud I have just shown, and you have, it's clearly moving to the right, but then you can ask what is its velocity, this cloud, this blue cloud. Can you describe the system when the system size becomes very large? So, okay, the thing you see, of course, if I would take n infinite first, then I would just have the branching Brownian motion I mentioned before. So what you really want to say is what happens if the time is very, very long, in the very long time, and then n very large. And in fact, it becomes a free boundary problem that I will discuss slightly later. And in fact, this was proved by Duret and Remnick and De Massy, Ferrari, and Presutti and Soprano. So these are the questions. What is the theory when the kind of mean field theory when n is very large? And the other aspect also I will mention, which was something we found very interesting, was the shape of the genealogical tree. That is, if you look at the population, so you have this evolving population, and at a given time, you have your blue population. See, time is going down. I have my population here, and I ask, what is the ancestry of this population? So I look at all the individuals, and then there will be a tree leading for this population, and I could be interested in characterizing this random tree by various ways. One way, for example, is to say I take my population and I take 2 individuals at random in this population, and there is a certain time t2 where I find their common ancestor. I take 3 of them. I have a time t3 and t4 and so on. And what are the statistical properties of these trees? And in fact, it turns out that these numbers have a lot to do with the theory of spin glasses and broken symmetry of replica. The numbers are exactly the same. I would just say a word about it. So the first thing is that it was proved by Berard and Guerre in 2010 that in fact the NBBM behaves exactly the same as the Fisher KPP equation with noise, with n being here. And therefore the velocity is exactly the same as what I mentioned before. So this was a mathematical proof. And the next thing is about genealogies. And to me, it's something rather interesting because it showed some kind of universality. And what happens is that if you look at the population at a certain time, at a very long time, and you ask what is the ancestry, now here I try to compare 2 situations, the NBBM that I have just introduced, and what would be a neutral model, that is, I want to keep the population fixed. So what I do is that whenever there is a branching event, I remove one of the particles at random without any bias due to its position. So this is what I call the neutral case. And if you look at the genealogies, then what happens is that if you make it neutral, then you get what's called as the Kingman coalescent. And if you take the NBBM, the trees you get, it's called the Bolthausen-Sneedman. And I will just explain what they are. They are different, but the Bolthausen-Sneedman is very well known in the mathematical community because it represents the trees which appear in the Parisi theory of spin glasses. Okay, so let me just say what they are. So again, I have my population and at a given time, and then I ask how far I have to go into the past to find a common ancestor to two individuals. And if I take 3, I have a time T3, that's I find the same common ancestor to 3 and T4. This is the quantities we have considered. You could consider other quantities for these populations, but this is one way to characterize. And what we obtain is that the following, is that if you take the NBBM or many other versions of it, for example, one version of it would be to say, I have a population of fixed size, and along the horizontal axis, the coordinate is just a kind of fitness. So I have population, I have many individuals, and each individual is characterized by its position, and its position is a fitness. And after one reproduction step, an individual has a certain number of offspring. It could be 2 offspring or k offspring, so it has some offspring, and each of them has some offspring. And at the next generation, I only keep the n rightmost. I want the population to remain fixed. And for this kind of model, both in simulations and for some particular models that we could solve analytically, we observed that the ratios of the time T2, T3, T4, T2 do not depend on the details, on how these etas are. You say that the fitness of the offspring is just the fitness of the parent plus some kind of noise. Now, precisely what the noise you have chosen here does not matter. You always find that these ratios are given by these numbers. And of course, you could compute times T5 and so on. And these correspond to what is called the Bolthausen-Sneedman. I'll just tell you what they are. And they are different of what you would observe if you had a neutral evolution, as I said before. Okay, so where was it? You see, neutral would be this. So I just kill uniformly to keep the population constant. And then the numbers are different. Now, just let me explain with words what is the Bolthausen and the Kingman coalescent. Okay, so this is a model of coalescent. So that's a way to produce random trees. There are many ways of producing random trees. So this is one family of them. And so at the bottom, I have my population. And I imagine that during every time interval dt, very short, most of the time nothing happens. But during a short time interval, each group in my population, each group of k points can coalesce into a single point with probability qk dt. So here you see that, for example, there is a group here of 5, and at a certain time that they will coalesce into one point. And then again, here I have a pair, it coalesces and so on. And at the end, I will end up with a single particle. And here I have a random tree. Now, what is the difference between Kingman and Bolthausen-Sneedman? In Kingman, all the QKs are 0 except Q2. So only pairs of branches can merge. So Q2 is non-zero, all the others are 0. Okay? So first, maybe what I should say is that if I give you the Q case and you want to spend an hour or two to think about the problem, then in terms of this Q2, Q3, Q4, you can compute all this coalescing time of the tree. So these are the formulas. They are not very important. But anyway, if the Kingman coalescent corresponds to situations where you have only pairs which can coalesce, nothing else. And if you take these horrible formulas, you put it in, and then you get T3 over T2 equals 4 over 3, and you get these numbers. The Bolthausen-Sneedman is the QK is Q2 divided by K minus 1. And you get these different numbers. And for those, I don't know whether there are experts of spin glasses here, but they know that, for example, in the structure of valleys in the spin glass theory, you have this coalescence with more than 2. You see, you have ultrametricity, but on top of it, you have the fact that the triangles, you have a certain fraction of triangles which have the 3 sides equal. And this is just what the Bolthausen-Sneedman says. So, okay, so this is the result of this n branching Brownian motion or its generalizations. They all have this universal Bolthausen-Sneedman trees in their genealogies. Okay, now let me just come to another aspect of it. You see, earlier I just said you take the NBBM when n is very large. It was proved by Duret, Remnick, and Demacy and other people that you get a free boundary solvable model. So now I'm just going to mention some works that we did with Eric Brunet in 2010, 15, and in these works we could find an exactly soluble case of a Fisher KPP equation. You see, the problem with the Fisher KPP equation is that you have the nonlinearities, and the nonlinearities, usually you cannot have explicit analytic expressions. Now, for mathematicians, they don't care. They can prove things with inequalities, but the physicists like more to compute things. Okay, so we found a model that we can solve and which has all the features that we saw in the Fisher KPP equation. So it started with a discrete version that I mentioned quickly now, and it leads to some interesting mathematical work that I mentioned. Okay, so imagine that I have my lattice and I have this U which evolve according to this equation. So it's a linear evolution, except that there is something nonlinear. So when U reaches the value 1, it sticks to 1 and it never moves again. Okay, so I have particle U, it takes the value 1, and then it takes some values here and they evolve according to that. And at some time, then the value 1 is reached and then continues, it stays in 1 at 1 here. Sorry, it stayed at 1 and then it moves like that. Now, it's not hard to realize that the first, okay, you take the value 1 up to a certain point, and then the next point, it's rather easy to solve because it's just a linear equation, differential equation up to the time it reaches 1. And the next one, it's also easy to solve. And so let me call Tn the first time that U at position n reaches 1. And the thing that we observed with Eric Brunet is that there is a way to relate the initial condition. There is this complicated formula. You don't need to understand it too much, to understand its origin, but it is an exact formula which relates on the left the initial condition and on the right the time at which at position n U takes the value 1. Okay, so it and hidden in this formula. So you just start with this formula, and when you do that, you can get the asymptotics of the time, so you can get that it moves at a certain velocity, plus logarithmic terms and so on. And all these terms, in fact, turn out to be exactly what I told you at the beginning about the Bramson and Hebert-Gonçalves corrections. So it just hidden that. And what we found 2 years later with Brunet and Berestik is that there is an even simpler situation, which is instead of doing it on the lattice, you can do it in the continuum. So this is just a free boundary problem. U has a linear evolution, except that when it reaches 1, it remains at 1. So this is just the equation. And we found the following formula, which contains, it looks not so complicated, but this is, for example, if you start with step initial condition at the origin, xt is the position of the front, it's the last point where u is equal to 1, and there is this relation here, and this relation relates the time here and the position. And this equation should be valid not for a single value of r, but for all values of r, as long as it says the integral is converging. Okay, so this is an exact relation between the position and the time. And now you have to do some analysis. It's a mathematical problem to say if this relation is valid for all values of r, or for an open set of values of r, what can you say about the asymptotics of xt? And the answer is here. It's exactly, you get 2t, the Bramson correction, the constant, the Hebert-Gonçalves, we could get another expression here, just everything is hidden in this box here, where there is this relation. Okay. Now, let me come, I think I have about probably 8 minutes or something. Is it okay?
Yes.
Okay.
Yes. Can proceed.
So let me just come to the problem of directed polymer, which is also, okay, it's a disordered system, and it's very related to the theory of spin glasses. And this problem of directed polymer, people have worked on it since mid-80s. And it's a very simple problem to formulate, but not so easy to solve. And imagine that I have a regular lattice, and the directed polymer of length L is just a path starting from the origin and going always down. And you imagine that on each, it's a disordered system, that on each bond of the lattice, there is a number, epsilon b, which is the energy. And this means that if the path goes through this bond, then the energy of the path will be the sum over b, the bonds visited, times epsilon b. So epsilon b are random energies, so there is a quench disorder, and then there is this energy of the path. And in fact, in '88, not some time ago, with Herbert Spohn, we just solved this problem on a tree. So we tried to make the mean field theory of it. So instead of doing it on the regular lattice, you see in 1+1 dimension, in fact, in d+1 dimension is related to the KPP equation. And in 1+1 dimension, a lot is known about this problem. But at that time, we tried to do it on a tree. And it turns out that when you do on a tree, you end up again with the Fisher KPP equation. So let me just say what it is. Here, okay, in the previous slide, I showed it for a regular tree. Here, I consider, again, the branching Brownian motion. And so after a certain time, I have a number of particles at certain position xi of t, and the statistical mechanics I want to look at is the partition function zt, which is the sum over all the branches, all the points of the Boltzmann weight here. Okay, so this is, and the tree is, so the sample is just this branching Brownian motion. If I take another one, then the positions xi, the xi are some quenched variables. Now, it turns out for this problem that, sorry, okay, it turns out, sorry, where is it? Yes, okay, it turns out that this problem can be again solved completely by the Fisher KPP equation, and I wrote here a recursion for this partition function. You imagine that you look at the very, very beginning, the very first time step again, and ever the particle moved a little bit, then the partition function is multiplied by exponential beta eta. Eta is just the shift, and or it branches and it's given by this. And what happens is that if you look at the generating function of the partition function, which is here, so you average over all the trees, then it evolves according to the equation for Q again. It's exactly the same equation that we have seen. Something striking about this fact is that the equation does not depend on temperature. And the only place where the temperature is hidden is in the initial condition. Now, if you remember what I said at the beginning, I said depending on the decay of the initial condition, then you might have a phase transition, because sometimes you were moving at a constant velocity, minimal velocity, or sometimes you had a velocity which depends on the decay. And here, this is the phase transition. The phase transition of the directed polymer is due to the initial condition, and beta is just in the initial condition. Now, the interesting, and so just from what we saw earlier, we can tell immediately what is the free energy in the high temperature phase and what is the free energy in the low temperature phase. And there is this Bramson shift, which is where the position of the front is. Okay. Just in the last 2 minutes, I want to mention that, in fact, this is, in my view, one of the simplest problems where there is a broken symmetry of replica, like in the Sherrington-Kirkpatrick model. In fact, here is a one-step broken symmetry of replica. Now, you have this branching Brownian motion, and now for each pair of points here, you can define Qij, their overlap, by saying for what is the fraction of the time the two paths were together. You see, you have 2 points, and if you go back in the past, there is a time Tij where the two trajectories merge. And the probability P of Q is just, by definition, 1 over z squared, and you take the weight of the first path, the weight of the second path, and then Q is their overlap. Now, since this work with Herbert-Spohn, we could show that this P of Q is not self-averaging, that it is consists of 2 delta functions, so it's very much, it's what's called the one-step RSB. But more recently, with Peter Motichot, we looked at what happens when the finite size corrections. And so what we found is that this one-step RSB, when you include finite size corrections that we could compute it without replica. We could compute it directly by using traveling waves. We get a formula, and what happens is that somehow finite size corrections produce a full RSB. Okay. Now, one thing I have tried many times, and I can say without success, is how to recover finite size correction, or this Bramson shift is some kind of finite size correction, or this P of Q here using replica. Never. The first one, it's very easy, but this, I don't see how to do it using replica and the Parisi theory. Okay, so this is what I wanted to say. I tried to convince you that these Fisher KPP equations have some kind of universal behavior. There is this Bramson shift, this logarithmic shift with the 3/2, and this you can see it in all kinds of traveling wave equation, always the same logarithmic shift. When there is noise, I told you that there is corrections like 1 over log n squared, and you find them in the noisy FKPP, in the NBBM, and so on, and they are there. The trees also, the genealogical trees I mentioned, are also universal in the sense that you change the rules and they are universal. And somehow what is, to me, are open problem, that none of these features, I can understand them ever using replica or using renormalization. Usually, renormalization is a way to find universal behaviors, but I don't know how to do it. Okay, so thank you so much for your attention.
Thank you very much, Bernard. Questions, yes. There is a question by Hille. Go ahead.
I'm here. Well, thank you, Bernard. I was fascinated by all your results, which are very striking. Well, one thing that really, I was struck of is this result where you have this. You replaced the nonlinear problem with the linear problem with the boundary with this v equal to 1. Is there a simple way to rationalize this? Why you get the same result as the nonlinear problem?
I think we get the same because, okay, somehow when you put the saturation at 1, it's linear, but the saturation at 1 plays the role of the nonlinearity.
Oh, I see.
And all the properties, the Bramson shift and all that, depend weakly on the nonlinearity. You might change the nonlinearity, and they don't change. There is what's called, there is there is, if you push the nonlinearities too much, then you get over universal behavior. And in fact, my paper of this year, which was published this year, is about what happens when you have a transition to over behavior. So,
okay, so you might expect that additional connection may give a difference then.
Yes. But the main answer to what you say is just that the nonlinearities are not so important. Okay, they should be there, but their precise.
The actual details of the nonlinearity does not matter. Okay, thank you very much. Yes.
Bernard, if there is no other question, I have a question, Bernard. You were mentioning at the end of your talk that essentially this way of approaching this problem of branching Brownian motion provides you how to say a way of understanding the replica problem in a different perspective, in some sense. So you have a way to approach it by these diffusion-like equations.
For this particular problem, for this directed polymer problem, yes. In fact, these are computation things. We compute the P of Q without doing any replica calculation. We get the result.
Yeah. So in some sense, the message is also, let me say if I misunderstood you or not, the message is that in this context, you have, how to say, tools that may approach the problem much more effective than standard usual things like replica normalization. So in some sense, you can tackle the problem mixing methods that in some sense provide you the answer to a very important question to my
but
understanding.
Somehow yes, but on the other hand, you give me the SK model, the Sherrington Kirkpatrick. I don't know how to write traveling waves for it.
Okay. So, but there might be some hope. Maybe, who knows? I mean,
yes, maybe. No, okay. Yes, there. Instead of saying there is some hope, there was some hope, because in the 80s, I worked on these random energy models and so on, and they can be solved by these methods, the generalized random energy model, and they have a number of features common with the true spin glasses, but it's not the Sherrington Kirkpatrick model. Then you need to ask Giorgio for it.
Yeah, okay. Okay, thank you very much.
Okay.
Are there other questions? Yeah, there is another one. Stefano Lepri.
Hello, Bernard. Stefano Lepri. Just a question about this large deviation approach.
Yes.
So you were able to compute the large deviation function, but I didn't get where the phase transition enters. It's just in the shape of this large deviation function?
Yes. Okay, let me just come back to it. Okay. Yeah. Yes. So yes. So it is on the. You ask what is the probability that the rightmost particle moves at a velocity v. And the form, okay, so if you, for example, you look at negative velocities, it's very small, the probability that the rightmost is moving to the left. And the answer are these equations. And this can be understood very easily, because what the system does, it has a strategy. You start with a single particle, and you want that the rightmost is here. How the system can do it? It does not branch for a long time, and then at some point there is an optimal time where it starts to branch. Now, what happens is that if you want the maximum to be much further to the left, what happens is that it will decide not to branch at all. So the phase transition is when you try to find the optimal time where it should branch, that this optimal time at a certain velocity, it decides that it is the final time. It does not branch. Or it just branches in the very, very late, but not at an extensive, you see, not at a time proportional to the total time. Is it clear what I say?
Yeah. So this means that there is a discontinuity in the large deviation function somewhere.
No, there is a singularity, which is
singularity.
You see, this is the large deviation function. If the velocity of the rightmost is between v star and 2, this is the expression, and if the velocity is less than v star, it's given by this expression. So you get two different expressions. In fact, it's rather interesting because the prefactors have strange power laws and so on. But I did not mention that.
Okay, thank you. Thank you, Bernard.
Okay, so thank you so much for listening to me. And
yeah, it's always a pleasure.
A little bit of Italy today, but no.
No, it was perfect.
Pleasure.
Other questions? I don't see any other question.
Okay.
Let's wait for a while, but okay, Bernard, thank you very much again for accepting our invitation. It was really a great pleasure to attend your seminar. I learned a lot, I must say.
Okay, so thanks so much for the.
So we'll see soon somewhere in Italy, probably, or somewhere else.
Somewhere. Okay, with pleasure.
Bye. Bye, Bernard. Bye.